Thank you very much. Of course, I would like to thank the organizers for organizing such a nice conference, and also all of you, all the speakers, because we've listened to some very interesting talks. So now let me tell you about continuous functions on Fedorchuk compacta. So let me start with the original construction by Fedorchuk from 1968. Maybe some of you know of it. And actually what Watson has argued in an article of 92 is that this construction is natural and that it appears and it is used sometimes even without explicitly knowing the construction. So this is a construction for constructing topological spaces. Fedorchuk used it originally to give some counterexamples in dimension theory. Later, it was used for many other things. So basically, what it is about is starting with some topological space and finding a way to put in some closed subspace, replace points by some other topological spaces. And this construction, I will not go into detail right now, but it gives you a way to replace all the points by some topological spaces. And he gave a generalization of this. So there is this property of a mapping. So let's say you have a topological space. Here, all spaces will be compact Hausdorff. A mapping between them is called fully closed if the intersection of the images of any two closed disjoint sets is finite. And what is important is that the canonical mapping from a resolution, so you start with some space Y, you perform this technique of resolution, you obtain another compact space X, and the natural mapping giving back the original space is fully closed. So what he actually did is he performed this construction iteratively. So he constructed inverse systems where at every level the mapping between the first space and the next one is fully closed. And then you continue this process and you obtain an inverse system which we'll call an F system. And moreover, if all the mappings, so if you skip some levels, continue to be fully closed, we will call this an F decomposable system. So the two concepts are not the same because a composition of fully closed mappings is not always fully closed, although this is the case for most classical, for all classical examples. So now, of course, if you say an F decomposable system is, you start with a point as it is written there. This is just a point. And you continue, of course, everything is the limit of an F decomposable system. Because this mapping is always fully closed. This is trivial. So it is natural to impose some conditions on the fibers of the neighboring bonding mappings, I will call these. So what Fedorchuk did, and what later Ivanov generalized, is the condition that all the fibers of the neighboring bonding mappings are metrizable. So we'll call this the limit of such a system. We'll call it a Fedorchuk compact or an F compact. And moreover, if the system is F decomposable, we'll call this an FD compact. So some examples. Here you have the double circle, a classical topological space, or the doubling of any compact space, a construction of Alexandrov. So here I have written how you can obtain the space from the circle by a resolution. So in particular, this is a Fedorchuk compact of spectral height 3. Spectral height, this will be the length of the inverse system that gives you the compact space. Another classical example, the double arrow space. And something that I learned yesterday from Professor Marciszewski's talk is that any separable compact linearly ordered space is also a Fedorchuk compact of spectral height 3. The construction that he showed us yesterday is exactly a resolution. In the same spirit, you have the lexicographic square. It's actually very similar. And here is a picture of what the topology looks like. And more generally, you have the lexicographic cube. So you perform this resolution many times, you get the lexicographic cube of height alpha, some ordinal number, and this will be a Fedorchuk compact of the same spectral heights. So now that we have seen some examples, let's see what the problem that I will be presenting to you is. So recall that a norm on a Banach space is called locally uniformly rotund if whenever you have a sequence of points in the unit sphere, one fixed point, a sequence such that the midpoint of the segment approaches the sphere, you need the sequence to converge to X. And this property has been studied extensively, and there are still many open problems in this direction. One of them is the natural question for which compact spaces K, the C of K admit an equivalent norm with this property, locally uniformly rotund. And this question is very old. There has been a lot of research on the topic. A complete characterization does not exist yet. There have been many examples, many classes of compact spaces for which this is true. And I will give you a couple of examples. Of course, I will not give most of them. I will give just the ones that are related directly to my talk. So in 1990, Hayden and Rogers showed that a scattered compact space of countable height admits, for such a compact space, C of K admits an equivalent Lure norm. Well, what we can observe is that any scattered compact space can be obtained as the limit of an F-decomposable system. And moreover, we have some nice property of the fibers of neighboring bonding mappings. They are homeomorphic to the one-point compactification of a discrete set. Another example, Hayden, Jane, Namioka, and Rogers, is that the lexicographic cube, which is like the canonical example of a Fedorchuk compact, well, it admits an equivalent Lure norm if and only if gamma is a countable ordinal. So the natural question is, does this hold in general for Fedorchuk compacta of countable spectral height? So again, here we have a counterexample whenever gamma is omega 1. So what has been done in this direction? So in 2020, Gurko, Ivanov, Shurikin, and Troyansky proved that whenever X is a Fedorchuk compact of spectral height 3, it admits an equivalent Lure norm. Then this result was generalized. It turned out that the metrizability, so again, let me remind you, because of the metrizability of fibers and that you start with a point, X1 is also always a metrizable compact space. It turned out that the metrizability is not needed. So to get Lure normability of C of X when you have Lure normability of C of Y, you only need Lure normability of the spaces of continuous functions over the fibers. But this does not solve the problem for an infinite spectral height. And so now what I will show you is that C effect, sorry for X, no, this should be C effect, admits a pointwise lower semi-continuity. This is not very important, the pointwise lower semi-continuity, but it admits an equivalent Lure norm whenever X is an FD compact space of countable spectral height. So you need this extra property of the full closedness of all mappings. And again, I will say that this is the case for all the examples that I know of. So now let me tell you what the main technique to prove such a statement is. So we have this characterization of Lure normability due to Molto, Orihuela, and Trojansky, which says that if you have a Banach space and you can decompose it in countably many pieces, such that for every point in every piece, you can find a slice of arbitrarily small diameter. Then you can construct an equivalent locally uniformly rotund norm. So the problem of Lure normability becomes a problem of finding such a decomposition and the appropriate slices. So now let me get back to the problem. Let me get back to Fedorchuk compact. So this is a characterization of a fully closed mapping in terms of a property of the continuous functions. So you have a fully closed mapping from X onto Y, and you have any mapping, a continuous mapping from X onto Y, and you can say that it is fully closed if and only if the continuous functions on X satisfy this property. So the oscillation over the fibers of Y is C0. So you have finitely many, for every epsilon, you have finitely many fibers on which the oscillation of the function is more than epsilon, which is a property that is very crucial for what we have been able to do. So let me tell you a little bit about how we can use this. So I drew this picture of the inverse system. So this continues. And let me draw another picture. Let me represent x0 as a point, which it is, and start drawing a tree which represents all the points of x1. So x1, all of its points are branches of this tree. And then we continue. And we continue in this way. Every fiber is represented, all the points of every fiber are represented as branches of this tree. And we obtain something in the limits. Well, this, I shall call this the tree of the system S. And we can, of course, we can do this for any inverse system. But what information does that give us? Well, not a lot. We don't have absolutely any information about the topology of the spaces. We only have some information about the points and where the mappings take us. Well, it turns out that this is not true for F-decomposable systems. So we do have some information about the topology. And we do have some information about the continuous functions over the limits. And the result is that whenever we take a continuous functions over the limits, let's say this is the limit, we have a continuous function over the limit, and we look at the lower levels. Well, these lower levels correspond to some points x in some level x alpha. We take the oscillation of the mapping over the corresponding fiber, and what we obtain, if we do this for all of them, is that this mapping phi, giving the oscillation over the fibers of every lower level, maps CFX into C0 of the tree of the system, if and only if S is an F decomposable system. Which is, I find this quite interesting, and the main idea is that this allows us to obtain a locally uniformly rotund renorming on the space of continuous functions over the limits. Well, of course, we need some more conditions. We need the metrizability. So I told you that the result is true for FD compacta. So we have this metrizability of the fibers between all levels. So now I have a little time, so let me tell you something more about the proof of this theorem. So now we need some notation. This notation, as you can see here, this gives us a quotient space. That basically, what does it mean? It means that if we have the space Y and the space X, we can think of it as obtained by a resolution from the space Y. Well, we can ignore some of the fibers. We can ignore some of the sets that we use to replace points. And we can do this for any subset of points of Y. So we can do the resolution again, but just for the points of some subset M. And if this gives us a Hausdorff compact space, this is equivalent to saying that the mapping is fully closed. And yeah, here is this proposition that gives us an equivalent definition of full closedness. And this will be very important. Here is an example. So you have here the usual square with the usual topology. Here you have the lexicographic square, and here you have this quotient space y for some point y in y. Well, here we can see that this topology is not Hausdorff. We cannot separate points that are on the non-trivial fiber, but here it is. So this is an example of how this works, and this is also an example showing that the mapping from the square onto the interval with the usual topology is not fully closed. And the idea is to iterate this. So we have the tree of the system. Well, okay, so this is here we have a diagram of two-level construction. This is perhaps complicated to explain in 1 minute. But here is something that is actually more simple, because I can draw it here. So let's say that we have this tree of the system S, and we consider a subtree, any subtree. Well, this subtree corresponds to the tree of a system, of another system, that somehow is contained in ours. Well, it does whenever the system is F-decomposable. So we can have this subtree, keep the fibers that correspond to the points of our tree, and we obtain, again, a Hausdorff compact space that is the continuous image of the one we started from. And maybe I should end here, but let me just tell you that this property of the continuous functions that I told you a couple of slides earlier, this basically means that if we take any epsilon positive, and we look at the tree where this mapping phi f of t is larger than epsilon. Well, this gives us a subtree, and moreover, it has finitely many leaves. And with this property, we can select finitely many functionals that will completely fix this subtree where the oscillations are large. And now that we have this property of fully closed mappings and this subsystem, we'll have a metrizable compact that is the continuous image of ours, and we can fix this with finitely many functionals, and this will give us the desired decomposition. So, thank you for the attention.